Welcome back, and today we'll be discussing the rectangular approximation methods for areas and volumes. It's a way of estimating the area under a curve. So basically this is a preliminary, conceptual preliminary to integrals. So there are three types of these approximation methods, and they are RRAM, so it's right rectangular approximation method, LRAM, which is the left-handed rectangular approximation method, and MRAM. So I'll get to what these mean right now. So let's say you have a curve, and it looks something like that, and you want to get the area underneath. You can split this curve up into several intervals, right? And you can, in the case, and you just split it up into intervals, and this is a basic way, and you can just find the area of these rectangles that you form. So the RRAM is when you use the right hand, the right side of the curve, and you make a rectangle of that height. So this would be RRAM right here, and you make these rectangles here, 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 and here. So that would be RRAM. When you split the curve up here, and then you use these intervals, and it's just base times height, and you add them all together, and you get your final sum of these areas. And LRAM is the same thing. So you have another curve. Just make it, but you use the left side. So again, you split it up into your straight subintervals, maybe of equal distance. Well, they should be of equal distance, and then you use the left side instead. So this would be one rectangle. This would be another rectangle. This would be another rectangle here and here. And the MRAM is when you're using the midpoint of these intervals. So this is RRAM, left-handed. This is the left-handed one, and the MRAM, the midpoint or the middle rectangular approximation method. So if you have another curve, again, just split it up into your regular subintervals, and you take the midpoint of each of these subintervals as the height to use, and then you make your rectangles using that height. So the midpoint here, use that height. Midpoint here, use that height. Point here, use that height, and this ends up. So these are three methods, and you just add together the areas of these rectangles, and you get an approximate value of the area under the curve. And this can be applied for many things in integral calculus. You use areas under curves a lot, and it can be used, like, for example, in a velocity curve. The area under this curve will tell you the distance that something has traveled. But this can not only be used for areas, but it can also be used as volumes. So say you have a curve here. We'll just discuss this conceptually. I'll do another example in my next video explaining this further. But you can also use this for volumes. When you have a curve like this and you're rotating around the x-axis, you can split this curve, it'll rotate, and it'll create somewhat of a shape of a cone, and you can actually split it up into its own cylinders. Like if you split a curve up, it'll be like this, right? It's three-dimensional because you've just rotated it around this, and you can split it up into its own little cylinders and find each volume of each cylinder like that, and then add them all together at the end in these separate segments. So that's yet another application of these rectangular approximation methods. But back to this one. So let's just do a quick example of this, and We'll talk more about the rest later. So let's say you have a car, and you're given the following data points, and it's a car that's accelerating from 0 miles per hour, or 0 miles per hour to 142 miles per hour in 36 seconds, or actually 0.010 hours. We will be using hours for this problem. So here's the data set. So you have the hours here and the miles per hour here, and the car at 0.0 is going 0 miles per hour, and then at 0.001 hours it's going at 40, 002, 3, 4, just write all these out. Alright, and at 1 it's going at 40, at 0.002 hours, 62 miles per hour. It goes to 82, 96, 108. So it's constantly speeding up, it's accelerating, and it's speeding up all the way to 146 miles per hour, which is where our data stops. Alright, so here's our table at the end, and this is going from 0 hours to 0.01 hours, or 0 hours to 36 seconds, and the question is asking to estimate how the distance that the car has traveled in this 36-second time period. So estimate the distance traveled in 0.01 hours. So we can just draw a sketch of a velocity time graph, because we do have velocity, we do have time, and then we can split it up into subintervals and estimate the distance traveled. So let's just set some guidelines for these subintervals. So let's split it up into 5 subintervals, and we'll use the midpoint approximation method, or midpoint rectangular approximation method. So we'll use the MRAM. Alright, so let's just draw the velocity curve I was talking about. So velocity on the y-axis in miles per hour, and here would be the time in seconds, and you have time in hours, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 0.0. Well, this is going to be 0.002 here. We'll just list every other one. 4, 6, 8, and that one, the last one. And it'll look something like this. It's just a car that's accelerating. So we can split it up into 5 intervals, and we're going from 0.002 to 0.01. We can just take every even one and just draw a line. So we'll just draw a line, and we'll split it up into 5 neat subintervals of the graph. And if you're using MRAM, which is what we want to use, we wanna use the speed at every odd interval of time that we have. So every 0.001 we'll use that speed, so that'll be 40, and then for here we'll use 0.003, and that speed will be 82, and we'll just go so on and so forth. So let's just draw these rectangles. One will be like that, the other one will be like that, this one will be like that. It's not too neat, but I think we get the point. We're using the height at this, and so just draw dotted lines here. And then we're going to find the area of these rectangles, and then add all these together to get the final estimate of the area under the curve, and the area under velocity time graph is the distance traveled. So as we continue with our estimate, Each rectangle will have a base and a height. So our base for each of these rectangles is actually the same. We have 0.002 as the base, and our height will vary. So let's just start out like this, and we can just multiply. Since we're doing this, we can just leave the 0.002 out, and we'll just multiply and add together all these heights. So at 0.001 it's 40, so we can add that there. Actually, we'll just make them separate rectangles, so make it easier to see how it is. So times 40 plus 0.002 times, this is the next rectangle, and this here is at 0.003, that's 82, plus 0.002 times 0.005, which is 108, plus the next base is 0.002 again, and the height at this point, which is here at 0.007, is 125, plus 0.002 times the height here, which is at 0.009, which is 137. So here we have it, our 5 subintervals, our 5 rectangular areas, and if we do add all these together, we end up getting 0.984. So the answer to this problem will be that the car actually traveled 0.984 miles in that 36 second time period of acceleration.